Hello and welcome to Math with Mrs. Becker. This is Algebra 2, Chapter 1, Section 1. Today we will be studying sets of numbers. One of the main goals for the day will be to classify and order what are called real numbers. We will be able to describe the various sets of real numbers and then describe those sets using various notations. Today includes a lot of vocabulary, so I did include a slide just to kind of show you some of the words that you will see as we work through the section. All right, without further ado, let's get started. Now, what is a set? A set is a collection of items, and every item is called an element. Okay, so again, a set is a collection of items called elements. And so one way that I really feel like this section will make sense is if you think of the game of pool or billiard. The rules of 8-ball, it divides the set of billiard balls into 3 subsets. Okay, so if you picture when you are playing a game of pool, there are solids. The balls that are numbered 1 through 7 are solid. There are stripes. Those balls are numbered 9 through 15. Then there's that darn 8-ball, and it is in a set all by itself. So these are subsets, and what that means is that within the larger set, which would be the entire set of all of the pool balls, you have subsets, so other little groups within the larger picture. The empty set, which is denoted by the circle with the little slash through, kind of like the no parking, no whining, all of those things, no cell phone signs. What that means is you have no elements that fall into that set. So for example, if I was still talking about the game of pool and I said the balls that are greater than 20, well, there are no balls numbered 20 or greater because they only go through 15. So if I were to say the set of billiard balls number 20 and higher, that would be an example of an empty set. Nothing fits that particular set. Now here's a really cool diagram. I love this thing. So every number that you have worked with so far in your life, in your mathematical career, they are called real numbers. Now you're probably like, what? Yeah, of course they're real. There are numbers that are called imaginary numbers, and in this course, you get to learn about those. Super cool. But for now, we're going to keep it real. Ha ha ha. Okay, so everything you've worked with, they are real numbers. And you'll notice that it's an R here. It's just a little shorthand way of writing real numbers, okay? Every real number is either rational or irrational. Now, irrational, again, has a shorthand way of writing it. It's the letter Q. Irrational, there is no shorthand. You got to write the whole word out. Now, every real number has to be one or the other. And in order to determine which one it is, I kind of like to think about conversations you have with people. If you have a normal conversation with a person, typically it makes sense. You know what you're talking about. It has an ending point to it. Okay, that would be rational. If you're looking at a rational number in decimal form, it either terminates, which means it stops, or it repeats. You know what's coming next. Now, irrational. Have you ever had somebody call you and they wanted to vent? That venting conversation may have been irrational. They may have gone on and on and on, and you had no idea what they were even talking about. When you look at irrational numbers, it's kind of the same thing. The number, when you look at it in decimal form, it's going to fill up the entire calculator, so it's never ending, and there is no pattern whatsoever. So I'm going to go ahead and show you what a couple of these look like on the calculator. So one example of an irrational number was -5 square roots of 3. So -5 square roots of 3. Look at that thing. It fills the entire calculator. There is no repeating pattern. That's why it's an irrational number. So rational numbers either stop or repeat in decimal form. Irrational numbers never stop, and there is no repeating pattern. Now, if something is a rational number, it may also be an integer. Integers, the shorthand is a Z, so I always say it as integers, kind of help us out there. I think of football. If you go to a football game and you listen to the announcers, you may have negative numbers. okay? You might have the quarterback get sacked, and so the ball has to go backwards yards, or there might be a penalty. You might have 0. The football may start and end in the exact same spot for a play. You may have a complete pass or a really good running play where you have positive numbers. So integers can be negative, they can be 0, and they can be positive. But one thing that you will not hear in a football game is the announcer use decimals. Integers do not include decimals. Okay, the next type of number, if it's an integer, then you can look and say, hey, if it's an integer, it might even be more than that. It might be a whole number, which can be shortened to W. Whole number, the way I think of it, is a donut, okay? So if I have a circle and I want to make it a donut, what you do is you punch out the donut hole. It looks like a 0. Whole numbers start at 0 and go upwards. 1, 2, 3. So whole numbers, again, no decimals. But what we did, going from integers to whole numbers, we eliminated the negatives. It starts at 0 and goes up. Now, natural numbers. If it's a whole number, it might actually be a natural number as well. Natural numbers are counting numbers. If you walk up to a young child and say count, they're going to start at 1. 1, 2, 3, 4, 5, and it's just going to continue. So the difference between a whole number and a natural number is that natural numbers don't include the 0. It starts right here. Natural numbers are n. The cool thing is, like if I take the number 2, 2 is a natural number because you use it for counting. 2 is also a whole number because it's 0 or up. 2 is also an integer because you can go 2 yards on the play in football. And 2 is a rational number because it stops. And it is a real number because everything that we work with right now are real. Super, super cool. So that's kind of where our lesson is going. We're going to start categorizing numbers. You maybe do want to keep this little chart handy as we work through things. It might make it a little bit easier for you. Okay, notice I just gave you one slide to show you those shorthand notations. R is for real, Q is for rational, Z is for integers, W is for whole, N is for natural. So if you do not see a shorthand here, like for irrational, you would have to write out the entire word, okay? Just in case you need to refer back to what is the difference between rational and irrational. I know I already described it in this video, but if you need to just go ahead and reread it, or if you kind of forgot, this is a good slide to refer to. It just kind of talks about rational, it makes sense. So it either stops or it repeats. Irrational, you don't know what's next. It doesn't terminate, it doesn't repeat, it makes no sense at all. And that's what I put here. Irrational, you don't know what's going on. All right, let's keep on going. So here is the first skill that they're going to have us do. It's kind of fun. We are going to be given numbers in various formats. So notice we have decimals, we have fractions, we have square roots, we have pi. They want us to be able to order those numbers from least value to greatest value. The best way to compare numbers is to put them all in the same form. And the format that would be the easiest would be decimals, okay? So 2.3 repeating. What that little line above the 3 means is that you are taking that 3 and you're repeating it. So in decimal form, 2.3 repeating, if I'm going to 3 spots, it's going to be 2.333. Okay, now pi is 3.14. Let's say that they want you to have more digits than that. There is a pi key on the calculator. So if I go ahead and I hit pi, if I want to go to 3 digits, it's 3.1415. Well, that 5 would bump it to a 2. So this would be 3.142. Now the square root of 5. Go ahead and calculate it. Square root of 5 is 2.236. I'm just going to go ahead and put that above. 2.236. Now negative 11 divided by 2. Okay, just as a reminder, how do you go from fractions to decimals? You take the numerator, which is the top value, and you divide it by the bottom value. So that is negative 5.5. So I'm just going to go 0, 0. Now this is already in decimal notation, so I don't have to do anything to it. So now if I'm going to order the numbers from least to greatest, I have to go ahead and look, okay? I only have one value that is negative, and that's the negative 5.5. but when you write your solution, you have to give the number in the notation that it was given to you. So what I mean is you're going to have to go -11/2 rather than writing it as a decimal. Okay, so whatever the form the number was given to you, that's the form you need to use in your final answer. Okay, so now after -5.5, the next smallest number would be 2.236, and I got that from the square root of 5, so I'm done with that. Next, I have a 2.3 and a 2.7. 2.333 is smaller. That came from the notation 2.3 repeating. Next, I would have 2.7652. That was the notation that they gave me. Last but not least, we have pi. So there's an example of ordering from least to greatest. Now what they want us to do is figure out what subsets they belong to. Now one thing, I said everything that we are doing right now is real. So you can go ahead and say boom, 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 boom. All of those numbers are real because you have not learned imaginary yet. You only know real numbers. So everything we look at is real. Okay, next, rational. Rational means that it makes sense. So this is 2.33333. Yes, it makes sense because I know the next number would be 3. Now, integer. Are you going to hear a football announcer say, and he went 2.3333333 yards on the play? No. After rational, if you have decimals, it's not an integer, not a whole number, not a natural number. If it's rational, it can't be irrational. So 2.3 repeating is real and rational. Now pi. Pi is real, okay, but check this out. It fills the entire calculator, and unless you have memorized digits of pi, I have 3.141592654. Do we know what the next value is? Unless you've memorized, you don't. It fills up the entire calculator. It doesn't stop. It doesn't repeat, so it's irrational. If it's irrational, it cannot be anything else. So pi is real and irrational. Square root of 5. If I look at the square root of 5 on my calculator, same thing. Look at that. It fills up the entire thing. The decimal is 0.236067978. There's no pattern. I have no idea what's next. Yes, it's real, but it's irrational. And if it's irrational, it can't be anything else. Okay, -11/2 was -5.5. Well, that's rational because it stops. -5.5, but it's a decimal. There are no decimals in integers, whole numbers, and natural numbers. And last but not least, 2.7652. This number stops. That's the end. So it's rational because it stops, but it's not going to be integer, whole, or natural because it's a decimal. You're not going to hear a football announcer say, and that was a complete pass for 2.7652 yards. I mean, that would be crazy. Nobody would even watch football if you had to hear all that. Okay, so it is only real and rational. Moving on, let's do one more because this is a big skill. Okay, so once we get to tests and whatnot, you got to make sure that you're really comfortable doing this. Okay, so first off, we want to be able to order the numbers from least to greatest. So again, anything that's not in decimal form, let's go ahead and do that. 2 is fine. Pi, let's just go 3.14. That's a decimal. 3 divided by 2 is 1.5. Now negative square root of 3 is -1.73. Okay, so again, when I write my values in order from least to greatest, I have to make sure that I go with the format of the number that we were given in the problem, okay, not the decimals that we calculated. The smallest value, we only have one value that's negative, so negative square root of 3, that would be first. Now if, oh sorry, there's actually two negative numbers, sorry. I have -1.73 and a -0.321. We're still good though, because this value is smaller. Next we have another negative number, so -0.321. Okay, now if I look what I have left, I have 2, 3.14, and 1.5. Well, the smallest is 1.5. That came from the fraction 3/2. Next, the next smallest number would be 2. And last but not least, again, we have pi. Okay, so listing numbers given to you in various forms into a line that goes least to greatest. Now again, we're going to go ahead and classify these. Every single one is real. Okay, rational. 2, it stops. 2, can you go 2 yards on the playing football? Heck yeah. Whole numbers, 0 and up, no decimals. 0 works. Natural, if you are counting, would you hit 2? 1, 2, absolutely. Okay, and again, it's rational or irrational. It can never be both of those. So 2 is real, rational, integer, whole number, natural. Super cool. Pi, we already had pi in the previous example. It goes forever and ever and ever, and there's no pattern to it. Now this, negative 0.321. This stops. This is the ending, so it's rational. It makes sense. It doesn't repeat and go on forever with no pattern, but it has a decimal, so it cannot be an integer, a whole number, or a natural number. 3 divided by 2 is 1.5. 1.5 stops. It's a terminating decimal, so it's rational, but it is a decimal, so it could not be an integer, whole number, or natural. Negative square root of 3. Oh, darn it, I had it on there. Negative square root of 3. This is what that thing looks like. Negative 1.732050808. And it looks like it starts to repeat here, but I have no idea because that pattern isn't found anywhere up here. So all I can say is, that don't make any sense to me. Okay, so that is the first thing that we look at in Algebra 2. Different sets of numbers. Can you order numbers from smallest to biggest? Can you categorize? Moving on to the next idea. One of the things they said is that they want us to be able to go through these sets of numbers in different types of what's called notation. Okay, so that means like going from numbers to words and words to what's called roster notation and set builder notation. Kind of fun. Okay, so again, if we're talking about the game of billiard or pool, if I'm talking about those numbers, I can use words and say the set of billiard balls is numbered 1 through 15. It tells me that I'm including all the numbers 1 through 15 in words. Roster notation, if you go to a sporting event and you look at a roster, what a roster does is it lists every single player for the event or every single actor or actress in the play. It's your roster. So if I'm going roster notation, rather than just saying, hey, 1 through 15, they're going to list every single one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Think of it as like a roster at a sporting event, or if you go to a play and you look at the program, they list everything. Okay, some other vocab words that it's important for you to understand. A set can be finite, like the set of billiard balls. Finite means that there's an ending spot. It doesn't go forever. The billiard balls have 1 to 15. So the main thing is knowing is that finite has a stopping point. But an infinite set, it's kind of like natural numbers. You start at 1, 2, 3, 4, 5, 6, 7, and as you count, as you get smarter, you can keep going and going and going, and you can count all day with no end, if that's what you want to do. So an infinite set doesn't have an ending. You can just keep going. Finite has a definite ending. Oh, I almost missed a page. Don't let me do that. Okay. Many infinite sets, such as real numbers. Real numbers is an infinite set because it includes everything that you've ever learned in math. It cannot be represented in roster notation. You can't list out every single real number. I mean, it's not even possible because there's so many. So there are other methods that you can represent these sets. One of the best ways is to use a number line. And so if I want to do the set of real numbers between 3 and 5, and this is kind of hard to see, so I'm going to go ahead. These would be open circles. The circles that I graphed are just really small, so they look like they're filled in. These would be open. We want the numbers between 3 and 5. They're open because you're not including the 3 and 5. You want all the numbers in between. But this is much easier to show that than if you try to do roster notation. You'd have to literally go like 3.00001, 3.0000011, 3.000000112 to any number that goes between 3 and 5. That's not even possible. So by doing a graph on a number line, you can quickly show that, or these are inequalities. This shows that your x value is in between 3 and 5. And if you look just at each one, this is x is greater than 3. We're going to the right of that. X is less than 5 because we're to the left of the 5. Okay. Interval notation. If you are ever considering going into college math, College math, one of the big things you really work with is interval notation. I love interval notation. What it does is it represents the area that would be shaded between two endpoints on a number line. There are two different types of brackets that you can have. If you are including the endpoints, you have squared brackets. So on the number line, your circles would be filled in. If you are not including the endpoints, you would have rounded brackets, and that means that it would be an open circle. One common mistake is lots of people look at this and they're like, hey, that's an ordered pair. Go to the right 3, go up 5. Well, yes, it is if you're working in coordinate planes. We're working on a number line. So what this means is we're looking at all the values between 3 and 5, but these are rounded, so it's not including those endpoints. That's what interval notation is. And again, college algebra, this is a huge topic. And you can go from this course, Algebra 2, to college algebra next year. So just one thing to kind of keep in your mind. Now, obviously, sometimes when you're graphing on a number line, you don't have two distinct endpoints. Sometimes you'll have something like x is greater than 2. So that means you'd have an open circle on 2, and greater than means it goes here. So what that means is that you would be going to infinity in your interval notation. Infinity is always rounded. Let's say you have x is less than or equal to -3. So from 0, I go 1, 2, 3. It is including it, so it would be a filled-in circle less than, so your interval notation, you always have the smallest value first. Infinities are always rounded, so this means it goes from -infinity all the way to -3. This is filled in. That would be the interval notation for this. Here, this would have been 2 to infinity. The 2 was open, so it was rounded. So yes, you can have infinities. Infinities are always rounded. Positive infinity means arrow to the right. Negative infinity means arrow to the left. So here's just a little chart that shows you that there are so many different ways that you can represent sets of numbers. So if I have numbers less than 3, well, that's using words. Less than 3 would mean open circle on 3, less than. Inequality, x is less than 3. Interval notation, arrow going to the left, so it's rounded, negative infinity. Open circle on 3, so it's rounded. So there are 4 examples just showing you how you can go from one notation to the next. And that's what we get to start doing right now. Put on your seatbelt, here we go. Okay, so they are giving us inequalities, okay? Those little Pac-Man alligator symbols, okay? We have to graph that on a number line. Do you know visually what that would look like? Okay, so on a number line, my numbers are going from 7 to 12. So I'll start off with that. 7, 8, 9, 10, 11, 12. Now you have to be able to figure out, okay, are they open or closed circles? Well, it does not include the 7. X is greater than 7, so that's a filled-in circle. X is less than or equal to 12. It is or equal, so it's filled in. X is in between the 7 and 12. So this set of inequalities means this on a number line. Then use interval notation. The smallest endpoint is a 7, comma, the biggest endpoint is a 12. If it's an open circle, it's rounded. If it's a filled-in circle, it's squared. Ta-da! Done. Let's look at another one. Now this one, I'm sorry, it's kind of hard to read. There we go. These are filled in and shaded between. This is open and going to the right, just so you can kind of see what we're doing. Now this is a graph. What they want us to realize is that there are 2 separate pieces. If there are more than one piece, you can have 2 separate intervals. So this interval, the smallest value is -6. It goes to the largest value, which is -4. And that's one big thing. Make sure that it's always smallest number, comma, largest number. Your endpoints have to go smallest to biggest. Now to figure out what kind of brackets, filled in, so they're both squared. Now here, my circle is open and it's in between 4 and 6. In between 4 and 6 is 5. Arrow going to the right means it goes to infinity. Open circle is rounded, infinities are always rounded. So that particular number line had 2 different intervals to look at. Here's another one. Use an interval notation. So this is filled in, just making sure that you see it, and it's going all the way to the left. So the smallest value is negative infinity. You always start off with the smallest. Arrow to the left is negative infinity. The largest value, the furthest to the right I go, is negative 1. It's filled in, so it's a squared bracket. Okay, this time they're giving us inequalities. They want us to draw a graph, then do interval notation. So notice I have different pieces here. The smallest numerical value I see is 2. The largest is 11. So I'm going to number from 2 to 11. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now I'm just going to focus on one piece at a time as I'm graphing. So this first one, x is less than or equal to 2. Less than or equal to, so it's a filled in circle. Less than goes to the left. There's one piece. Now x is greater than 3, so that's an open circle on 3. X is also less than or equal to 11. Less than or equal to is filled in. The x is in between the 3 and the 11, so I shade in between the 3 and the 11. Now again, notice I have two different sections or two different shaded regions on this number line. That means when I go to interval notation, I have to have two intervals. So here, arrow to the left, that's negative infinity. To 2, 2 is colored in, so it's a squared bracket. Now here, the smallest value is a 3, to the biggest value it's 11. 3 is an open circle, so it's rounded. 11 is a filled in circle, so it's squared. Okay, so far we've really looked at words, number lines, inequalities, and interval notation. Here's one other way. It's kind of cool. It's called set builder notation. And I am going to be honest, it's one that you really don't see that often beyond this class, unless you take like a graduate level math course in college, which, hey, you might. But it is kind of cool to see that there are other ways that you can represent these sets of numbers. Now, set builder notation is very, very specific. You have to start off with one of these funky looking brackets. The words for that is the set of. That's what that bracket is. Now the x, you're going to have a variable. All numbers x, a vertical line, which is read such that. Then you have an inequality, some kind of inequality. And x is, then you have to say what kind of number it is. And in this case, x is a natural number. Remember, natural numbers means you start at 1 and you go upwards, no decimals. So this is representing in set builder notation the set of striped billiard balls. Okay, so it's 9, 10, 11, 12, 13, 14, 15. Notice there are no decimals. There are no zeros. There are no negatives. That's why it's natural. So it's bracket, the set of all numbers x such that. X is in between 8 and 15. It doesn't include an 8. It does include a 15. And we're looking at natural numbers, meaning no decimals. Okay, so that's what set builder notation is. So the big finale for 1.1. They're going to give us one notation. We need to write it out in whatever notation they tell us. So this is set builder notation. They want us to write it out in words. So remember, with set builder notation, that little bracket is the set of. X is all numbers x. The vertical line is read such that. So every single time you go from set builder notation to words, 100% of the time, it will read the set of all numbers x such that. Every time, no exceptions. Now it's, how would you read that inequality? X is greater than negative 5.5, and x is n, remember z is integer. So what that means is they would have to eliminate the decimals. It can be negative, it can be 0, it can be positive, but that set of numbers in particular is not looking at any decimal representations. Okay? Positive multiples of 10. Now what a multiple of 10 is, it means you start with 10 and you multiply by 1, then by 2, then by 3, then by 4, then by 5. They want it in roster notation. Roster notation, think of the roster you get when you go to a sporting event. It has to list everybody. So 10 times 1 is 10. 10 times 2 is 20. 10 times 3 is 30. 10 times 4 is 40. Now, this is an example of an infinite set. We could sit here for the next 40 minutes and take 10 times 5, 10 times 6, 10 times 7, and just keep going. However, you probably have better things to do, okay? So what you do is, if it's an infinite set, meaning you can keep going on and on and on, you do a few, and then you end with dot, 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 means that that particular pattern continues, okay? Next, they're giving us a number line. This is supposed to be right on the -2, and notice the arrow is going this way, okay? Set builder notation, bracket, X, vertical line, every time. Now what you need is an inequality to describe the numbers that you're looking at. We are looking at X being less than or equal to -2 because it's a filled in circle and it's going to the left. Now, X is what kind of number? Notice this is an arrow filling in every single value. So all we know is that it's a real number because this is shading any value less than -2. So that means it's going to include negatives and decimals and fractions and all those things. So if it's shaded on a number line, it's going to be a real number. Okay, let's do a couple more. 2, 4, 6, 8. How would you write that in words? Obviously, there's lots of ways that you could do that, okay? You just want to make sure that whatever wording you have will get you to the numbers 2, 4, 6, and 8. And notice there's no dot, dot, dot. So it starts at 2 and it ends with 8. So I'm going to say multiples of 2, because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. So those are multiples of 2, starting with 2 and ending with 8. You could say the first 4 multiples of 2. You could say even numbers from 2 to 8. All of those things would work because if you were to take that description in words and write out the numbers, you would write 2, 4, 6, 8. Okay? Here's another one. Now this is roster notation. So roster notation, we need to write out everything. So we have set builder notation. We want all of the numbers that are natural numbers, meaning they have to be positive numbers. They're not negative, they're not 0, and natural, we don't deal with any decimals. So natural numbers that are in between 2 and 8, but they don't include 2 and 8, so I can't include that. So it'd be 3, 4, 5, 6, 7. Those are all of the numbers that are natural numbers in between, not including 2 and 8. Okay, set builder notation. So bracket, X, vertical line. Again, if you are a visual learner like I am, it helps me to do this. If I have 99, this is a filled in circle. This is supposed to be rounded, sorry. I got excited and put that funky bracket going to the right. So bracket, X, vertical line. Now it's the inequality. X is greater than or equal to 99. They have no restrictions. So what we're looking at is it can be anything. It could be 99.99999, 99.9999998. It can be 100.003. They did not give us any limitations, so the only thing that we know is that X is going to be a real number. Okay, we have completed 1.1. I know the notes were kind of lengthy. Typically, I would say that they will probably be around the 25-minute range. Day 1, there were just a lot of vocab things, and I wanted to make sure that I explained it in a manner where you understood things. It's never fun to start a class and be confused, okay? So tomorrow is just a work day. If you are in the classroom, you get the whole class time to work on the book assignment. If you need help, I am here to help you out. If you are online, you do not have any notes to watch tomorrow. Tomorrow is a work day on the assignment, same assignment. You're going to go to 1.1 in the textbook. Remember, there is a link in Google Classroom as well. Your assignment is to complete those 33 questions, and that will be a notebook check, meaning I just need to see that you tried every single question. If you have any questions or you need any help, feel free to let me know. I hope you had a great first day of Algebra 2. Bye.